11th, a magnetism and magnets. 11th.1, History of Magnetism. Magnets mystified the ancients. In Magnesia, Asia Minor, the early Greeks found lodestones, which baffled them with their strange ability to attract and hold iron particles. The Greeks were among the first to describe magnetism. The ancient Chinese made similar findings and were equally entranced. To these people, magnets seemed magical. Some suggested that magnets were evil objects possessed by invisible spirits. Others claimed that magnets could heal sickness and cure headaches. In the Middle Ages, the superstitious believed that owning a magnet endangered your health. Possessing a lodestone might brand you as a wizard or a witch and earn you a fiery reception from an angry crowd. Yet it was during this time that practical uses for magnets were first discovered. As early as the 4th century BC, the Chinese recorded that pieces of lodestone seemed to align themselves in favored patterns. Fortune tellers made great use of these mysterious rocks. The Chinese eventually carved lodestones into spoon-like shapes so that their handles would point south when resting on a flat, smooth surface. Around AD 1100, they developed navigational compasses using magnetized needles. Until then, sailors had navigated using visual observations of the sun and stars or by measuring water depth. A sudden storm, an overcast sky, or deep water robbed sailors of these navigational aids, and sometimes led them to their deaths. The magnetized needle compass may have been imported to Europe along the trade routes from the Far East, or it could have been independently invented there. Inventive and learned Europeans and Arabians soon designed crude compasses that gave travelers more accurate direction. In these compasses, the needle was magnetized to point north rather than south, as the Chinese compasses did. In 1269, Petrus Peregrinus de Maricourt wrote in a letter to a friend that a spherical lodestone exhibited two separate spots where bits of iron collected. From this observation, de Maricourt reasoned that the magnetic properties of the lodestone were concentrated at these two locations. He also noted that they seemed to be opposite in nature. Today, these two areas of concentrated magnetic force are called magnetic poles. De Maricourt suggested that the Earth's north and south magnetic poles resided in the heavens above the polar regions, rather than on the surface of the Earth. Despite de Maricourt's findings, myths regarding magnetism abounded throughout the Middle Ages. In 1600, the English physician William Gilbert put these ideas to rest. He conducted many experiments and compiled a book on the properties of magnets, known or suspected at that time. He explained that a compass behaved as it did because the Earth itself was a magnet. Some of the facts in Gilbert's book, such as the medicinal properties of magnets, were based more on his ideas that magnetism was the soul of a magnet than on observational evidence. Yet Gilbert brought the study of magnetism into the realm of science. 11th.2, Magnetism and magnetic fields. Is magnetism produced by magnetic charges, just as the electricity is produced by electrical charges? This question directed the efforts of many early investigators. They supposed that these magnetic charges could be separated onto different objects, just as positive and negative charges can be isolated. Thus, an object could have only one type of magnetic pole, called a monopole. No one has ever observed such an object. Magnetic objects always have a north and a south magnetic pole. They are magnetic dipoles. If you cut a magnet in half, you will end up with two smaller magnets, each with a north and a south magnetic pole. Scientists have found that even when magnets are divided as many times as physically possible, each of the microscopic fragments has both a north and a south magnetic pole. Even the molecular structures that form magnets exhibit a magnetic dipole. Despite a continuing search, no one has demonstrated the existence of magnetic monopoles. Magnetism, like the electrostatic force, is a field force. A magnetic field can be modeled using magnetic lines of force, which are similar to an electrical field's lines of force. Field lines clump together at magnetic poles and spread apart farther from the poles. Unlike electric fields, which begin at positive charges and end in negative charges, magnetic lines of force are modeled as continuous loops, both within a magnetized object as well as in the space around it. See Figure 11-6. The direction of the field line is determined by the direction a tiny compass would point if inserted into the field. Magnetic field lines point away from north magnetic poles and toward south magnetic poles. The distance between field lines indicates the strength of the field at that point. Thus, the field is strongest near the poles and weaker at points between the poles and at greater distances from them. Magnetic fields interact with each other, just like electrical fields do. When north and south magnetic poles are brought close to each other, the lines of force bend toward the approaching poles, and the objects are attracted. The lines of force point from the north pole of one object toward the south pole of the other. If like poles are brought near each other, the field lines bend away from the approaching poles and the objects repel. From these observations, we obtain the law of magnetism. Opposite magnetic poles attract, like magnetic poles repel. 11.3 Magnetic Properties. Magnets that you are familiar with are made from a small group of metal elements and alloys. These exhibit the property of ferromagnetism, and they are called ferromagnetic materials. Such materials include iron, nickel, cobalt, and a few other elements. Interestingly, liquid oxygen is also strongly ferromagnetic. Steel, an alloy of carbon and iron, and alnico, an alloy of aluminum, nickel, cobalt, and iron, are commonly used to form the strong permanent magnets used in motors and speakers. Alloys of certain rare metals, such as neodymium, make the strongest permanent magnets. Large versions of these magnets are hazardous to handle because they can severely pinch fingers and folds of skin. Smaller neodymium magnets are used to hold some jewelry, such as earrings, in place without piercing. According to the accepted model, magnetism originates at the particle level. Some atoms are tiny magnetic dipoles due to the arrangement of their electrons. Large groups of magnetic dipoles automatically align in the same direction to form microscopic regions called domains. In unmagnetized ferromagnetic materials, the magnetic directions of the domains are oriented randomly, so their magnetic forces cancel each other throughout the material. When an external magnetic field is applied to ferromagnetic domains, they align with the lines of force. When it is removed, the domains remain aligned to form a permanent magnet. The atoms of paramagnetic materials don't reside in domains and are randomly oriented. An external magnetic field will cause their atoms to align, but as soon as the field is removed, the atoms return to a random arrangement. Paramagnetism refers to those materials that are only slightly attracted to magnets. These substances, such as aluminum, magnesium, sodium, and gaseous oxygen, are said to be paramagnetic. The strength of the attraction of paramagnetic materials often varies with temperature. Figure 11-10 contrasts the effects of ferromagnetic and paramagnetic materials on magnetic fields. When a ferromagnetic iron bar is placed in a magnetic field, the lines of force are concentrated in the bar because the field is strengthened as it interacts with the ferromagnetic materials in the bar. When the magnetic field is removed, the bar usually retains some magnetism. This residual magnetism is why steel sewing needles or paper clips can be magnetized by being stroked with a magnet. A paramagnetic material's effect on an external magnetic field is weaker. The field is not strengthened as much by its presence. Also, when the external magnetic field is removed, paramagnetic materials do not retain any residual magnetism. However, as long as the field is present, paramagnetic objects act like ferromagnetic materials. Natural magnets, such as lodestones, display ferrimagnetism, which behaves somewhat differently from ferromagnetic materials. A lodestone is made up of compounds of oxygen and two different kinds of iron. One kind of iron atom has a magnetic field oriented in one direction. The other kind has a field oriented in the opposite direction. The two kinds of iron atoms are mixed together in the mineral. Since each kind .s present in different amounts within a piece of lodestone and since each has a different magnetic direction, The two magnetic properties subtract. The resulting magnetism of the lodestone is the net difference of the two kinds of magnetism. A fourth magnetic property is diamagnetism. Males weaken an E6 turn Ma magnetic ICLD by centerating Zen oppositing. In a field diagram, the lines of force are dispersed slightly as they pass through external magnetic, the diamagnetic material. All forms of field matter are naturally diamagnetic. However, many common substances also have natural atomic and molecular magnetic dipoles, which produce ferromagnetic and paramagnetic responses, the effect of diamagnetism to an external magnetic field. Since the effect of diamagnetism is many thousands of times smaller than that of ferromagnetism or paramagnetism, non-magnetic materials. Diamagnetism is observed mainly in diamagnetism can produce some interesting effects. Diamagnetic atoms. An external magnetic field causes poles that align to oppose the external magnetic field. If the external field is strong enough, the diamagnetic effect can produce a measurable force that acts opposite the magnetic field force. Figure 11 to 13 shows a small, approximately 6 millimeters, sheet of artificial graphite that is highly diamagnetic. The strong magnetic field from the 4 neodymium magnets resting on a steel base act on the graphite to generate an opposing magnetic field in the graphite that lifts it above the magnets against gravity. 11.4 Magnetism and Temperature. Since magnetism originates at the particle level, temperature can significantly affect it. You know that particle motion increases with temperature. This motion tends to disrupt particle order. Ferromagnetic domains, such as those in iron, normally maintain a high degree of order due to alignment of the magnetic dipoles of the element's atoms. However, at 770 degrees Celsius, 1043 Kelvin, or 1418 degrees Fahrenheit, iron abruptly loses its ferromagnetic properties. The domain boundaries dissolve, and the atoms assume completely random arrangements. This temperature is called iron's Curie temperature. Each ferromagnetic material has its own characteristic Curie temperature. A sample of iron above its Curie temperature WW will behave like a paramagnetic material when placed in a magnetic field. 11.5. The Earth's magnetic field. What makes a compass point north? William Gilbert showed that the Earth itself is a gigantic magnet. Its magnetic isle is aligned in a generally north-south direction. A compass contains a very light bar magnet mounted on a pivot point so that it can turn easily. This bar magnet aligns itself along the north-south direction of the Earth's magnetic field, as the needle spoles sect the opposite magnetic poles in the Earth. Did you know that the Earth has 2 north poles? The geographic North Pole is at the top of the Earth at the axis of the Earth's spin. This is sometimes referred to as true north. All lines of longitude intersect at the geographic north-south poles. The magnetic North Pole is where the Earth's concentrated magnetic field lines are vertical at the Earth's surface. It is nearly 470 kilometers, 292 miles, away from the geographic North Pole. Its position is not constant, but is currently drifting nearly 40 kilometers per year towards Siberia. Compasses are attracted to the magnetic North Pole, not the geographic North Pole. In some parts of the world, the difference is important. In Bangor, Maine, your compass would point 170 degrees counterclockwise from the direction of true geographic north to magnetic north. If you lived in Barrow, Alaska, magnetic north would be 18 degrees clockwise from true north. Is the magnetic North Pole of the Earth really a north magnetic pole? Remember that it attracts the north poles of magnets. Are the north poles of magnets attracted to other north magnetic poles? No. The Earth's magnetic North Pole is actually a south magnetic pole. This may require some mental adjustment to understand, but it has little impact on the use of magnetic compasses. The Earth's magnetic field originates deep inside the Earth, probably due to the flow of liquid iron in the Earth's outer core. This field extends far out into space. Near the Earth, the geomagnetic field deflects or traps the high-energy charged particles of solar wind. Without the geomagnetic field, these particles would bombard the Earth's atmosphere and surface, damaging or destroying life. Creationary scientists point to the existence of the geomagnetic field as just one of several characteristics of the Earth, favorable to supporting life that were designed by an omniscient creator.